Hey everybody, in this video we're going to go through the first couple questions of the AP Calculus Readiness Review Assessment. So number one gives us this function and asks us about the end behavior. What happens to the function as x gets close to infinity? And so as I think about this, I know that the numerator is squared. The degree of the numerator is 2, and the denominator is linear, so its degree is 1 here. And the basic rule is that I actually don't care about this minus 4 and minus 1. And if you think about it, as we approach infinity, if this is 10,000 or 10 million, and we square it, and then we subtract 4, it just doesn't matter. Same down here. You got 10 million minus 1. We don't really care about the minus 1. Yes, it's going to change the answer, but not by a lot. So I can really just say, okay, I don't actually care about these things here. And then my function is x squared over x. And now, again, it's not equal to it, but it's almost the same. Minus 4 and minus 1 does change the answer. But when x is big, and only when x is big, this is about the same as just x squared over x, which is just x. And so if we're talking about x going to infinity, then the function also goes to infinity. And again, the logic here is when x is huge, this minus 4 and minus 1 just don't matter. 10 million squared minus 4, who cares about the minus 4? You know, the classic math teacher way to say that is if Bill Gates drops $4, he doesn't even notice. Okay, he's got $10 million squared here. 10 million minus 1. These just don't matter. Only when x is big. If we're not talking about approaching infinity, that logic does not apply. But because we are talking about approaching infinity, we can sort of ignore those. We say, all right, well, let's just look at the first term. What does that simplify to? Well, it just simplifies to x. So as x approaches infinity, so does f of x. Think about it in the same way for number 2. Well, now this minus 3 doesn't really make a difference, and you just have x over x. Well, that's 1. No matter, well, and again, it's only when x is huge that I can subtract this, or that I can ignore this subtracted 3 here. So this function basically, when x is big, we'll write that out this time. When x is big, f of x is approximately x over x, which is 1. Now for both of these, you may remember your rules from pre-calc or math 4, that if the degree in the numerator is larger, you're going to go to infinity. If the degree in the numerator and denominator are the same, you're going to go to the ratio of the leading coefficients. And those are fine rules. As we see in the next example, those rules aren't always helpful. So if we remember those rules and we remember why they work, and that's what we've been explaining, kind of ignoring this minus 4 and minus 1 when x is huge, ignoring this minus 3 when x is huge, then we really have a good understanding of what's going on here. All right, the next two, numbers 3 and 4 here, it's the same function, just flipped upside down. So in the first one, we have e to the x in the numerator, x squared plus 1 in the denominator. In number 4, it's flipped. And again, we're thinking about end behavior. And in this case, we've split it up into the end behavior on the left as we go to negative infinity, and the end behavior on the right as the x goes towards positive infinity. And again, what this means, I should have maybe been a little clearer. When we talk about end behavior, we're saying what if the inputs are going towards negative infinity, if the inputs are getting larger and larger numbers but negative, what are the outputs doing? What's happening to the output of the function? As the inputs approach positive infinity, what's happening to the output of the function? And we have to think real carefully about e to the x here. And if we think about the graph of e to the x, let's draw a quick graph here. Now this is a function that we should know from Math 4 pre-calc. The graph of e to the x looks, sorry, excuse my stylus there, without the squiggles, the graph looks something like that. And just thinking about the e to the x, as we go to the left, as the x's goes towards negative infinity, the values of e to the x, the outputs of just the numerator, will go towards 0. If I think about x squared plus 1, well, that's just a parabola that's been shifted up 1. Again, excuse my squiggles there. X squared plus 1. So what you have here in the number 3 function, when the e to the x is on top, you have basically 0. As x approaches negative infinity, the output of the numerator is going to go to 0. This is about 0 over, well, and then the green one, that's a big positive number because we square it. So it turns it back positive. And if you have something really small divided by something really big, you get something really small out. You know, it's just a tiny fraction, 1 over a billion. That's a small number. And it's just going to keep getting smaller and smaller as the x's go farther and farther to the left. As the x's go farther and farther towards negative infinity, this numerator gets smaller, the denominator gets bigger, so your fraction overall is going to get smaller and smaller and smaller. So this is going to go to 0. As x approaches positive infinity, well, now we've got both of them are big positive numbers. As the x goes to the right, both the numerator and the denominator are getting large. But if you think about your functions, and my graph is not perfect here, this e to the x is going to pass that x squared after not too long. Exponential growth will always pass up polynomial growth. Just plug in a couple numbers on your calculator and do e to that number versus that number squared, and you'll see that after you get past like 10, if not even sooner, the e number will be much, much, much larger. So we have, for this second one, we have a huge number over a big number. And that's going to be a really big number. It's still going to be big. That's still going to be infinity. Because, again, you've got a billion divided by a million. Well, that's still a big number. And it's just going to keep getting bigger and bigger and bigger and bigger and bigger and bigger. As the numerator gets bigger, the denominator gets bigger, they're both going to just keep getting bigger. Nothing's going to make it go down to 0 or some other smaller number. Number 4, again, we take those same two equations and we just flip them over, flip our numerator and our denominator. So as we go towards negative infinity, well, my e to the x is still going to 0, but now that's in the denominator. So now I have a big positive number over basically 0. I'm going to say approximately 0. Well, if you take a large number, let's take a not that really that large number, but large enough. If we take 100 and we divide it by a half, you get 200. So as that numerator keeps getting bigger and the denominator keeps getting smaller, your output just gets bigger and bigger and bigger and bigger. So this is going to be a really big number. We call that really big number infinity. Now, going the other direction, now we have x squared plus 1. That's a big number when the x's are big. Very technical terms here. But then the e to the x, that's an even bigger number. Huge number. So if you take a pretty big number, pretty big, x squared plus 1, put in a large x, you're going to get a pretty big number out. 1,000,000 squared is huge. But e to the 1,000,000 is so much bigger. So you take a pretty big number, divide it by a way bigger number, you're going to get something small out. And that's just going to get closer and closer and closer to 0. So that's 0. Now, it's a little trickier here to think about this because of the e to the x. But if you really think about it, it follows the same rules as our polynomials. So if we look up at our polynomial, this x squared, that was saying the numerator is bigger than the denominator. So when the x's get big, when the inputs get large, this big number is going to be big enough so that the outputs will still stay large. That's the exact same logic as right here. Oops. They're both getting big as we go to the right, but this one's much, much, much bigger. As we go to the right, as we plug in big numbers for x, both of these are big, but the one in the numerator is so much bigger. And if you take a huge number and divide it by a pretty big number, the output is still pretty big. That's the logic here. Okay, so we're just, even though we have e to the x, you can just treat it as almost as if it's a, x to the 99th, because that's essentially how it behaves, at least when you're going to the right. But when you're going to the left, it's going to 0. So you have to take into account there both sides. And that's why we split it up into two pieces here. Okay. So that's the first 4. Check for another video for the next couple problems.